So Genevieve is the speaker, which kind of came from the furthest. She's from Australia, where she studied, and she's just leaving Belgium, so we got the last chance to hear her speaking. So lucky us. She's also a scientist, so we have another academic talk. After that, we're going to the industry, or dark side, which I like to call it. Genevieve is a neuroscientist, so she likes to pick your brain. So we saw how we can find out from the distant planets, and now we're going to see how data looks like in your brain. So go.
All right. So just come 40 light years back down to Earth, and now come inside your own head, and that's what we're going to talk about here. So in my work, I work with brain data, so that's the type of data that I want to talk to you about tonight. How we get it, why it's interesting, and one way that in our group we try to make meaning from it. So what is brain data then? Well, in very simple terms, brain data is a measurement of brain activity. So in my work, I'm interested in how the brain responds to faces. So I might show you a face that's interesting, like this one, and while you look at it, I'm going to measure your brain activity. So ideally, I'll take a very small electrode and we'll just pop it right down inside your brain, hook it up to an amplifier, and record the electrical impulses generated by your neurons every time they fire. That would be ideal. As you might imagine, though, that's not the best thing from an ethics perspective, so usually what we do is something a little bit more like this. It's a good proxy. This is electroencephalography, which is more or less the same principle, except on the scalp. So here we're going to record electrical activity from any number of sensors that we place here on the scalp, and all we're measuring really is voltage change over time, which then we look at here in either a time domain context, like you can see here, or we transform it and look at it from a frequency perspective. So why would anybody care about that type of data? Who, in fact, cares about that type of data? Well, scientists like me care, mostly because we're interested in knowing something about how humans behave the way they do, or indeed why they behave the way they do. But it's not just science doctors who care, real doctors care too, of course. You can tell they're real doctors because they're all doing the real doctor work that they teach them in medical school. So in a hospital setting, EEG brain data is used to do things like identify seizure activity or to determine whether a patient might be a good candidate for surgery. And then finally, there is now also an increasing commercial interest in brain data. Maybe you've heard of neuromarketing. This is this idea that companies have where they would like to use brain data to gain insight into consumer behavior or consumer preference. It's a burgeoning field as well. Okay, but from a scientist's point of view, working with brain data is really a lot like working in mining. And by that I mean you spend a lot of time underground in very dark, windowless places. And then you bring your data back up to the surface, and then you spend time sorting it and sifting it and trying to figure out which bits are rubble, which bits are important, and what you're going to do with them. And then finally, once you've polished everything up and it looks nice and it's in a good package, your real job is, of course, to convince other people that what you dug up is actually valuable, which is a pretty good metaphor for what it's like to publish in science. Okay, but it's worth remembering, though, that brain data in and of itself, or actually any data for that matter, isn't especially meaningful just by itself. I can put electrodes on your head, but I won't be able to read out any thoughts or ideas from it. I have to be able to ask the right questions. And that's what I do in my job as a cognitive neuroscientist. I try to think of clever ways to ask the right questions of brain data to learn something about human organisms. So I'm going to tell you something about how I try to ask those questions in my research. I work on perceptual categorization, which is a fancy way of saying knowing what something is that you are looking at. So whenever you open your eyes, you're hit with this kind of barrage of complex visual information that's changing all the time. And yet, within that overwhelming data stream, you can classify what you're looking at very, very rapidly. It takes you no time at all to know if it's an animal, a vehicle, a building, a face, and so on. When you think about it, the efficiency of that process is actually very, very remarkable. Synthetic systems don't begin to approach it. So that's what I'm interested in, that's what I work on. But how do we actually measure perceptual categorization? Well, one way is to take advantage of the brain's sensitivity to periodicity. So in my experiments, I show participants displays that look like this. It's a stream of object images that appear at a strict periodic rate of exactly 6 Hertz. And I achieve that periodicity by modulating the contrast of each image such that I get 6 per second, and I present all different types of object categories: animals, buildings, vehicles, plants, what have you. Now, in and amongst all of those object categories, you might notice that there are faces. In fact, the faces actually kind of jump out at you. What I'm really interested in my work is knowing something about how the brain dissociates faces versus objects. Faces are a particularly important type of object for the brain, and that's what I work on. How do you know that something is a face out there in the world? So the faces don't appear here at random intervals, though. They're actually also fixed in their periodicity. They appear as every 5th image in the sequence, which you can see here. And what that means then is there's 2 stimulation frequencies in this presentation. 6 Hz, which is the base image presentation rate, and 1.2 Hz, which is the frequency with which faces actually appear. So if I record EEG while you view a very boring sequence like this one, this is the type of result that I can expect. Here's my frequency spectra. Here I have amplitude on the Y and frequency below. And what you can see right away is that my flickering image stream elicits a very, very strong response at the exact frequency of presentation, which is 6 Hz. And it's usually here over the back of the head where the visual part of the brain is. Now that entrainment response arises because every time a new image appears on the screen, you have an evoked response in your visual cortex that corresponds to the arrival of that image. And since I stagger the images at fixed intervals from one another, I force that evoked response in the brain to also be periodic. And what that means then in practical terms is that I concentrate the signal into a single frequency bin, I don't allow it to disperse over the other frequency bins, and that gives us this very high signal-to-noise ratio here on my 6 Hz frequency. Now, of course, what's really interesting, though, is what these signals represent. I call this 6 Hz frequency a common response in that it reflects aspects of visual processing common to both faces and to objects, because it's simply the updating of visual information with each new image that arrives. What we really care about, though, is there going to be any distinction between a response to a face and a response to some other class of object? And we have an easy way to get at that here that also draws on periodicity. So remember that the face images appear as every 5th image in the sequence. So if the brain is indeed responding differently every time a face comes along, as opposed to any other type of object category, then that signal should be concentrated here at 1.2 Hz. And of course, it typically is in our types of designs here. So we can refer to this as a face selective signal. And what it reflects is ostensibly the brain's capacity to make a distinction between the 2 types of objects or 2 classes of stimuli that I contrasted in my experiment. So here, this particular response, it's reflecting the distinction between faces versus objects. If indeed the brain responded the same way to faces as it does for any other class, then all of that response would be captured at 6 Hz, and we wouldn't see any frequency response here at 1.2. Incidentally, that response, because of the nonlinear way the brain is responding, is also reflected in harmonic frequencies of that 1.2 Hz response, which, if I consider them globally together, provide me a way to quantify the degree to which the visual system is discriminating faces compared to objects. So that's the type of work that I do, but obviously the paradigm is broadly applicable to any 2 classes of stimuli that you might want to compare. So the sorts of questions that we answer in our group using this periodicity-based approach, obviously here I've spoken mostly about faces versus objects, but other people in our group are doing very interesting things with emotion recognition, wanting to find out what's the capacity of your visual system to distinguish between different types of facial emotion, not usually with Kanye, usually with much more boring cases like this one. And indeed, other people are extending the work to totally different types of visual processing with respect to reading, lexical processing. So there's some people in our group who are working on trying to understand how it is that children's lexical ability changes across the developmental trajectory, and they're using exactly the same type of periodicity-based approach to understand something about how different types of word stimuli are processed at different ages. So in this instance here, you have a bunch of non-words and interspersed at regular intervals with real words. And if you find, in this case, obviously we don't look for a face selective response, we look for a word selective response. And then we're able to quantify it and make comparisons across age groups, or indeed before and after training, that sort of thing. So these are the sorts of questions that the periodicity can be useful for with respect to brain data. I'm sure I've hit my time, so I'll wrap it there. Thank you very much.